Wait. Hello, hello. Okay, good afternoon, everybody, and welcome back to DSP. Welcome back to DSP. So today is our second week of lecture, and we will have a first discussion session tomorrow. Okay, tomorrow we have the first discussion session, and please notice that I've posted homework number one. Okay, homework number one is you can download it from e-class, and it will. There are going to be 3 questions. So I've asked my TAs to help creating a sign-up sheet online. Okay, sign up. Yeah. So you will need to answer. So please look at the 3 questions right here. And if you're interested in volunteering to be showing your solution on in the stage, please sign up. Okay, please make sure that you receive the notification from the TAs, and you'll need to sign up. And we will have, as I promised, we will have an English session as well as a Chinese session, Mandarin session. Okay, 国语啊. Yeah. So, any question regarding that? Regarding what's going to happen tomorrow? And yes, please. Yeah. Yeah. So the question is, can I select one session to attend? The answer is yes. You don't need to show up both. You are welcome to stay if you choose to first attend the English session first. Yeah. Is that clear? Yeah. 怎么样？ The question is, if I sign up for both Chinese and English, does the probability increase 2 times? You're welcome to do so. I cannot promise. I taught probability before. I need to calculate. I need to talk to my TAs. Yeah. But the short answer might be yes. This is the first ever discussion session, right? So we are not going to spend time to make sure that we exclude your, come on. We're not going to be so careful. but you're welcome to try to sign up for both. Yeah. But please show up, right? Okay. But another question might be, do we announce who are selected beforehand? Last year, is Jason here? Because Jason is one of the TAs who took this class last year when he was an undergraduate. 他在隔壁是 Yeah. So we'll figure out. Will we announce the result of random selection before we meet, or will we not? I'm not sure. I think last year we didn't announce. You just come into the classroom and the TAs will write down the ID number. 学号写黑板上了. That's a moment. Huh? 3个前会公布的. Okay, so the answer is we will announce it. Okay, so you can make sure whether or not you are selected. Okay, yeah. But let me just quickly tell you that there are 3 questions. Okay, the first 2 questions will use DTFT, the discrete-time Fourier transform, but we haven't officially introduced it yet. It will happen today. But I am here, so I'm assuming that if you have taken signals and systems, this is not new to you. Okay, discrete-time Fourier transform. So the first question will ask you to derive the DTFT of a time domain signal in discrete time. Okay, so that's just calculation. You do need to use the definition of DTFT. So if you want to work on it as early as you can, you might need to refer to the textbook or to signals and systems. Okay, so that's the first question. And the second question is the opposite. I ask you here to calculate the inverse DTFT of a spectrum. So you're given a spectrum or a frequency response. And I ask you, this is something similar to a low-pass filter, but not quite, not exactly. But here I ask you to calculate the inverse Fourier transform. So basically to go from frequency domain back to the time domain. Yeah, using the inverse of DTFT. So those are the first 2 questions. But otherwise, the third question is related to today's lecture for sure. It's about interpolation. So later we are going to show that the ideal way to convert discrete time back to continuous time is to perform a kind of interpolation by the name Sinc, the Sinc interpolation, S-I-N-C, Sinc. Okay, the Sinc interpolation. But here I designed a problem where you are going to study not Sinc, but simply linear interpolation. Now, linear interpolation has been done a lot, right? A lot of time we use linear interpolation to explain things. Okay, so it's a very natural way to process a signal. But here we want to argue that linear interpolation might introduce some spectral distortion. Okay, so it's not recommended. You can do that, but it's not recommended. So those are the three questions that we're going to discuss tomorrow. Right? So with that, let me just switch back to the. Thanks for the questions. Yeah, help clarifying things. And so let's just go back to the lecture slides. Lecture 3, lecture 2, probably right here. And I will need to show just the PDF and full screen. Okay, yeah, full screen. Right? Right. Okay, so let's start lecture number 2. D to C conversion. And we treat it as a kind of interpolation, Sinc interpolation. So here is a bit of recap. So just let's restart this slowly. So we have the beginning point really is a signal in the time domain, in the continuous time domain. Okay, yeah. Continuous time domain with a continuous time variable t, right? And we argue that when we sample it with a sampling period, so essentially what's been done is to convert the signal into a train of spikes, a sequence of spikes. And we call the result x after sampling, small x. Yeah. Where's the eraser? We call the result after sampling to be, rename it x sub s of t, and it's defined as the signal of our interest times something we called s of t, where s of t is just a infinite sequence of delta function with the same height 1, okay, and summation over all n, all integer n, okay. So that's the definition of the function, the s of t right there. And so now we consider. So last week we spent some time to calculate to convince us that the Fourier transform of the result, when we multiply two signals, these two signals in the continuous time, and we take the Fourier transform, the result is going to be a spectrum denoted as big X, and turns out that it will be equal to an infinite summation over this index k, and it's going to be the original spectrum, but shifted to the right and to the left. Omega minus n times k times, not n times, k times omega sampling rate, essentially. And there is also a normalization factor, a scaling factor, I should say, a scaling factor that's simply there. Yeah. So that's the correct way. And we show that, so that's like what it looks like in an equation. But last time we also showed that we want to make a sketch, make a drawing, right? Make a drawing. So what's happening is that if we just make a sketch of this, what's happening here in the frequency domain, and we very soon realize that as long as our signal is band limited to begin with, we assume that the bandwidth is, do I have a bandwidth right here? If the bandwidth is 2 pi times b. So always be careful that here, sometimes when we talk about bandwidth, the unit matters. So here the unit, I'm assuming the big omega, right? Big omega has a unit of radian per second, which is 2 pi times hertz, okay? 2 pi times hertz. So I say bandwidth B in hertz, then as long so the criterion is that as long as the sampling rate is at least 2 times higher than B in hertz, then we are pretty good. Okay? So that is to say, what will happen after sampling is a infinite summation of the spectrum to the right, shifted to the right and to the left. Okay? So as long as our sampling rate here, omega s, equals to 2 pi, which equals to 2 pi sampling rate. Yeah. As long as it's bigger than 2 pi p, 2 pi b, bigger than 2 times 2 pi b, then these shifted copies are not going to overlap. And we like it, right? And we like it because the spectral shape is not going to be changed. The spectral shape is preserved, 是保持住的. So we're happy about that. So we like it. Also, on the negative frequency side, we have everything is symmetric. So let me just draw another one copy. But conceptually, the summation extends to both directions. Okay? Very good about this. So we also, and this is good because, so now the question is, how do we go back from the sequence of spikes back to the continuous time? We want a reconstruction. 我们希望重建. We want a reconstruction from the spikes. The spikes now is already a lot is missing. Everything in between spikes, everything here is missing. Everything here in time is missing. So we need to reconstruct. 要重建起来. We need to construct it, get it back. Right. So the question is, how do we get back the continuous time, a copy of a reconstructed signal, so that the reconstructed signal will be the same as the signal before sampling? Okay. So let's talk about frequency domain operation first. Okay. So this is what's recommended. We recommend that we can introduce low-pass filtering. We can introduce low-pass filtering in the frequency domain. That is to say, we multiply. I suggest that we multiply the entire extended spectrum with the yellow thing right here, 黄色, the yellow thing right here. Okay? So the yellow thing right here is a low-pass filter. Low-pass filter, so that we want to only keep the middle copy while rejecting everything else. Because the middle part here is what we begin with, right? The original band-limited spectrum. So we want to keep only the middle part while rejecting everything else. Rejecting all the extra copies of the spectrums which are sifted elsewhere. We want to reject all those high-frequency components while keeping only the middle part. So this is a low-pass filter, and we want the low-pass filter to introduce no spectral distortion. That is to say that the gain here needs to be constant, so that there's no distortion. The gain here has no distortion, while in the stop band, everything is 0. Okay, so that's an ideal case. So that we call this frequency response an ideal low-pass filter. So do I have the equation right here? So let's try to read the text right here. So conceptually, we use a low-pass filter for reconstruction. Reconstruction from what? From the samples. From the samples back to the continuous time. As long as the sampling rate, still we need to emphasize this. We can do that And we are guaranteed to have a perfect reconstruction only if the signal has a finite bandwidth to begin with, and we sample it at least 2 times higher, at a rate that is two times higher. Okay? But with that, then in this lecture, we're going to look at more details about this low pass, and in particular, we calculate the inverse Fourier transform of the low pass response. Okay? We go from here is in the frequency domain, but we go back to the time domain. Okay? So to do that, we need to calculate the impulse response of this reconstruction filter. And later we point out that we have an interpretation, 有个诠释一个角度啊。The way we look at what's going on here in the time domain is that we point out that this low-pass filtering actually corresponds to interpolation. 中文叫内插啊 interpolation is nothing but interpolation. So why is that the case? First, we need to show write down the frequency response for the low-pass filter. Okay, so here that's the next slide. So we recommend that in this low-pass filter, which I'm going to denote as H, here's the frequency response. So let's be specific. So H, as I said, should be constant in the passband and 0 elsewhere. 0 outside, constant when the frequency is below pi times sampling frequency. That is the Nyquist rate. Because 2 pi times that is the sampling rate in radian per second. So pi times that is 1/2, right? So here I'm suggesting that the cutoff frequency right here really is pi times sampling rate, which is half of that. Okay? We recommend that we define a ideal low-pass filter with a cutoff. This is called the cutoff. The cutoff frequency in radian per second is pi times the sampling frequency. That also corresponds to the Nyquist rate. Sometimes we call half the sampling rate Nyquist. It goes by the name Nyquist, or this Nyquist rate. Nyquist rate in radian per second. Okay. So with that, this definition and the gain here, it happens that we recommend the gain to be exactly t being the sampling period. Okay. All right. So from this, is that clear? The definition. Okay. Low-pass filter with constant gain t. But why t? Why t? The reason is because when we multiply our frequency response with this thing right here, when we multiply, take the product of the sample spectrum, the spectrum after sampling, with the frequency response, then just by looking at the equations, you should be able to figure out what will happen. You should be able to figure out that what we get is exactly just the middle part, and we have the right scaling factor right there. Okay, this a long story short, t. This t right here cancels with this 1/t. Right? There's 1/t right here. Is that clear? 1/t right here and here. If the gain is t, then the two of them, when we take the product, the result is 1. Okay, so that's one tiny detail. It's not the most important, but here is my explanation why the scaling factor is t right here. Okay? Because this t will cancel with the factor here, 1/t. Okay? And what's remaining is really the middle part with the right shape, no distortion, and the right amplitude everywhere. Okay? Is that clear? Right magnitude everywhere. 那个正负是对的啊。The magnitude will be right at every frequency. Okay? Is that good? Yeah. Should be able to notice that either from drawing or from the equation, we will be able to figure out that, sure, it should be clear that when we multiply a low-pass filter, we keep only the middle part, which is the original spectrum. Keeping only the middle part. That's the idea. Okay, so if we just move on to the second point right here, so this is what we call filtering. I need to emphasize, okay, at least to in my career, when I say filtering, it's a multiplication in the frequency domain and convolution in the time domain. Almost always, okay? So That's technically the term, what it means in signal processing, in the signal processing lecture. I'm not sure in other field, you filter coffee, is it a low-pass filtering? Yeah, no, I'm not sure. But in signal processing filtering, 滤波 is always, it always means to multiply our spectrum with a frequency response. Just nothing more, nothing less, multiplication. In the frequency domain, that's the definition of filtering. Can we agree on that? Okay? Can you agree on that? When we say filtering, is a multiplication in frequency. Sometimes in certain applications, we also multiply a signal in time with another envelope in time. Multiplication in time domain, sure, you can do that, but let's not call it filtering. Let's call it something else. But when we say filtering, it's a multiplication in the frequency domain, which corresponds to convolution in the time domain by a theorem. Okay, there is this convolution theorem which tells us that we can achieve filtering by convolving one of them with the other. Okay, so here the idea is to convolve our result of sampling with the impulse response, what we call an impulse response. Impulse response, and what is the impulse response? The impulse response is the inverse Fourier transform of the frequency response. So that's how we call them. So the impulse response, small h and big H, they form a Fourier transform pair. One in time domain, the other in frequency domain. They form a Fourier transform pair, 一个对偶, a pair. Right. So impulse response is the inverse Fourier transform of H, of big H, which is defined right here as a constant in the pass band, 0 in the stop band. That clear? So far, so good? So about all the terminologies right here, we want to make sure that we agree on all the terminologies. All right, so but with that, the next question, what's the next question? The next question is now we are ready to do the calculation. Okay, we're ready to derive the inverse Fourier transform. Make the calculation. Let's do the calculation next. Okay, let's calculate together what's the inverse Fourier transform of this thing, the big H. Okay, because it's important. So next thing, let's do this together. Probably over there. Okay, so we are going to calculate the inverse Fourier transform of the desired frequency response. Okay, so here in the middle, I use some like bluish color right here to indicate a mathematical formula that we introduced for the first time. Okay, you can also find it on the textbook for sure, but here I want to just introduce that the inverse Fourier transform can be calculated this way. So here we have the desired response, and we need to go to the time domain. And the way we do that is to consider this as the gain to a small wavelet at exactly the frequency, the corresponding frequency. And then we are going to collect everything together by integration. Okay? This is a gain which will happen to any selected signal at this frequency, any signal at this exact frequency, so that when we collect everything in the frequency domain, we do an integration from -infinity to infinity. All the frequency are going to be collected together, okay, using this idea. Okay? And there is also a factor 2 pi that should not be missed. Okay, is simply there. So that's the inverse Fourier transform. Sometimes we can also use this notation with a script f, 草写的, the script f to denote Fourier transform. And with the -1, that's the inverse, right? Inverse Fourier transform. Inverse Fourier transform of any given spectrum is defined. Okay, I'm running out of space. It's defined as 1/2 pi times the integral. 1 over 2 pi times the integral. And we need to get the result. Just to jump to the conclusion, it turns out that when we plug in h right there, you will get the result right here. Okay, so let's do it together. Okay, let's spend some time to do it together. Okay, so 1 over 2 pi, we are going to do it together. So first of all, what is h? H is constant, right? H is constant, so the constant is what? The constant is t. So t times e j omega t, and the integration is with respect to big omega. But h is t only in the passband, right? Only in the passband. So that now the lower bound, lower and upper bound for integration should be from the cutoff frequency within the within that bandwidth. Okay, so the integration should happen from minus pi sampling rate to pi times sampling rate. Yeah. Minus pi sampling rate to plus pi sampling rate. Okay, so next we can just organize everything a little bit. Here's t, there's 2 pi, and now this is pretty simple. This is simply exponential. So in the exponential, we know how to do the integration, right? So let's just be careful. I want to be careful. So here is jt 1 over that, and e j omega t with omega lower starting frequency right here, ending final frequency right there. Okay, that's just integration. Antiderivative. That's a term I'm missing. 反导数. Just to figure out the antiderivative of this function. Right? In the integrand here, we are integrating with respect to big omega, not t. Okay, so let's just be careful. That's why we pull out this constant, jt, right here, shows up right here. The factor shows up right here because we're finding an antiderivative, 反导数, antiderivative. So far, so good. So now let's just push up forward one more step. T still here, 2 pi still here, jt is still there. But now here we mean exponential j pi sampling frequency t minus exponential j this frequency times t. Yeah? Okay? Minus exponential j that frequency t, and we close the parenthesis. Yeah, okay, so yeah. So here, for those of you that know, just by applying Euler's formula, what is Ej something? Ej something is cosine that thing plus j sine that thing, right? Yeah. So when you just subtract the two of them, what you get is 2j times sine of that thing over there on the exponent. 在那个指数的地方 exponent. Okay? Pi fs t. Okay, so hopefully so far I'm still correct. Okay, so now what's going on? So we have t over 2 pi still here. Jt is still there. But on top, now we have 2j sine pi times sampling frequency times t, which is a function of t, right? The inverse Fourier transform is a function of t, okay? Small t. So now we're almost there. Almost there. So just cancel j cancel 2, right? So now what do we have? Now we have sine pi times sampling frequency. What is sampling frequency? Sampling frequency is by definition 1 over t, right? 1 over t. So here really we have divided by big T, and just be careful, multiplied by t, okay? Divided by what? At the bottom we have exactly the same thing, pi here. If we just move the big T right here to the bottom of bottom, to the denominator, 在分母的地方啊。The denominator, then finally we get this expression. Isn't that the same as here? Yeah, it's the same. So that's the way I make the derivation, right? A function of t. That's what we get back in the time domain. Okay. So far so good. Yeah. So that's a simple exercise, hopefully. And now, so here. We also, I love drawing sketches, yeah. So I learn things by drawing. So now you're sure we have this beautiful thing, sine of something divided by that thing, and but how does it look like in the time domain, right? How does it look like in the time domain? Yeah, how does it look like in the time domain? Maybe I can erase this part. So next thing. We want to be careful to draw a sketch, right? To draw a sketch. So now h of t is sine of pi t divided by big T divided by the thing, same thing, pi t divided by big T. But let me mention that here we have a small problem. We have a small problem because when t approaches 0, when t is 0, this expression is not defined, right? You notice that when t is 0, we have a 0 at the denominator, and we cannot divide things by 0, right? So I need a suggestion. What do we do? Can we apply L'Hopital's rule? L'Hopital 法则好不好啊 L'Hopital rule, anybody? When t is 0, let's define. This is when t not equals to 0. So when t is 0, let's apply L'Hopital's rule. L'Hopital. Yeah, you can apply L'Hopital's rule, or yeah, it's not necessary you need to do that, but let's define that when we apply L'Hopital's rule, because the sign of something equal to that thing when that thing is very small, right? When that thing is approaching 0. So let's define this to be 1 at t exactly 0. So here, this is why we're going to try to make a sketch. Okay, we try to make a sketch right here. Yeah, but you know what I mean, okay? It's going to be 1 at when time equals to 0. Okay, so we already got that. So 1 when time equals to 0. And the next thing is to realize that what? To make a sketch, we should expect h of t to approach something when t approaches infinity. H of t should approach 0 when t approaches infinity. Can you agree on that? Yeah. Because simply t is right here, right? Sine is bounded. Sine is bounded, right? So when t approaches infinity, we should expect to see an envelope like that. An envelope also in the negative part. And this is an even function, 左右对称, an even function. It has an even symmetry. All right. So so with that envelope and 1 at time 0. So next thing is to figure out there are going to be 0 crossings of h of t in h of t. H of t is going to cross 0 horizontal infinitely many times, okay? Because there is a sign component on top, right? So it's going to alternate sign. So every t, every multiple of t is going to change its sign. So in the first t right here is going to go to 0, and then it's going to cross and change polarity and then go back to 0 at 2t. And at 3t, we expect it to again come to 0, and let me just 4t and so on. While the envelope, the amplitude is going to be, should I say, attenuating, okay, as t approaches infinity. So that's on one side. On the other side, we have exactly the same thing. H of t turns out to be an even function. Okay, so let's just, for the sake of completeness, minus t, minus 2t, and so on. We expect the signal when we draw sketch goes negative and then positive, crossing 0 at integer multiple of t, and so on. So that's a simple sketch. You can do it by yourself, right? So that's how this impulse response looks like. Okay, so from now, by now we have completed the derivation as well as making a sketch. Okay, so far so good? So far so good. And what are we doing right here? Why do we take this calculation? Because this is an impulse response, right? And we are going to use it. How do we use it? We are going to use this impulse response and convolve it with a sequence of spikes. That's what we are going to do. Okay, we're going to do, because the purpose. There's a purpose. The purpose was to make a D to C conversions to reconstruct the signal back in continuous time. Okay, let's be reminded. Let's remind ourselves that's the purpose. Okay, so in the middle step, we need to figure out that this is the h of t that we're going to use for convolution. The next thing we're going to show to study what will happen when we convolve this Sinc function with a sequence of spikes. Okay, yeah, with any arbitrary sequence of spikes. All right. So a few remarks right here. As I mentioned, the function sine theta divided by theta is often called and denoted as the Sinc function, Sinc. So we write Sinc of theta. We really can, you feel free to do this. Okay, feel free to do this. But be careful that we also need to define the function at time 0. Okay, so let's define Sinc function at 0 to be 1. Okay, and it also so to make everything continuous. So now this Sinc function is also continuous in time. And by the previous slide, we show that h of t now in this notation is simply Sinc of what? Sinc of pi t divided by big T. Okay? And now we use the notations. H is Sinc. And now our task right here, the next task I would like to invite you to do is to make a sketch of convolution. Okay? Make a sketch of convolution. And convolution of what? Convolution between two things. Okay? We're going to convolve H with the result of sampling. What's the result of sampling? The result of sampling is to multiply our signal of interest with the spike train, with the delta function, the spike train right here. Okay? Yeah. So what is going to happen? What's going to happen? Yeah, so I do have a highlight, okay? But I may need to use the board right here, okay? So let me erase this. So here now next, let's draw another sketch. Now in this sketch, we are going to visualize. We're going to visualize convolution of exactly these two things. The first thing is the spike train. Which has been the result of sampling a continuous time signal with a fixed period. Right? We sample the continuous time signal with a fixed. I'm not doing a very good draw right here, but with a fixed period, you know what I mean. In continuous time. So now this is what we denote as here. Okay, multiplying the continuous time signal with the spike train, and the result is denoted as x sub s. Okay. So let me say this is x sub s, and the continuous time signal here, original signal has been denoted as x sub c, emphasizing that it's continuous. Okay, emphasizing that it is continuous, and s stands for sampling. After sampling, before sampling, simply put. Okay. Now, all right. So now we want to visualize what's going on when we convolve this with h. What is h? H is sinc. Okay, now h is sinc. So first, I have this suggestion. Okay, I do have a suggestion right here. So I suggest that sure, x of s is by definition the multiplication of xc with the spike train. But there's another way to write, to express x sub s. There's another way to express x sub s. How? So here's my suggestion. You might want to realize that the other way which is also correct, is to consider summation n on the outside, but inside we have x n times delta n minus, no, not n, t minus n times big T. So that's my recommended way of writing it. Okay, my recommended way of writing, and you can check if this is correct. And I claim that this is also equivalent. This is equivalent. This is equivalent. Why? Because the height of each spike, if you take one spike, each spike has the height, 那个高度 has the height. How tall is it? It's exactly so tall, right? xn. For example, if this is time 0, then this is the height of this spike is x0. And if this is t, then the height of this spike is x1. And so on. So if the height of this is n, if this is time n times big T, the height here is x of n, and so on. Because that's how we define sampling. Sampling is to evaluate the signal at integer multiples of t, right? And this is how we denote the result, right? Because this is correct because x of n has been defined as x of c evaluate at integer times big T, n being integer. So this is a correct way of thinking about the, yes? 哪里？这里面。Right. So here I need to be, yeah. So the question is whether I should write down n or nt. Is that your question? Yeah. So I think I'm using this notation. Okay. When we look at the continuous time signal, which is denoted by x sub c. Okay. So x big N with bracket, 中括弧 bracket. When we use the bracket, then what's inside here can only be integers. That's a very good question. Let's clarify our notation. It could be confusing. Yeah, I agree it could be confusing. But when we use the bracket, 用这个中括弧 when we use the bracket instead of parentheses, 小括弧 or parentheses, when we use the bracket, the inside is a discrete time index, which we assume in the textbook. The authors assume that this n really is an integer and nothing else. You cannot plug in x bracket 1.5. That's not allowed. That's not even allowed. So that's why here I just use n instead of nt. Whereas you're sure x of n stands for xc at nt. For sure, you are correct. You are right about that, on that. Okay, is that clear? Does that answer your question? Right. So I really like this expression because it allows us to see. It emphasizes that the result of sampling is going to be a sequence of spikes, each having this height, each having a different height. And we just collect the height, record the height, and call it a sequence of numbers. That's what's happening in sampling, when we convert the signal from continuous to discrete time. So I really like this expression. It's just spikes shifted to the right and to the left, but and modulated by the height, which has been sampled, okay? Which has been measured. So I like this expression. Both are correct, but we are going to rely on this expression in the following derivation. Okay, so can we agree on that? That this is also the correct. This is also a correct expression for what's going on after sampling. Okay, it's also a correct. Yes. 哪个地方？这里吗？No. Okay, so the question is, should we I put nt here or simply small t? Okay, so the reason I put small t is to emphasize that the entire thing here should be considered as a function of time for any t as a real number. So here t is still continuous, but here the tricky thing is that here n is discrete. So that may take a while. That may take a while to understand our notation. Here we emphasize that this is a continuous time signal, even though it's almost zero almost everywhere. Even though that it is zero in between, but in between here you can still talk about x sub s. It's simply zero, right there. But in here we cannot talk about x of anything fractional. 不能讲小数点，不能 n. You cannot take n being a non-integer. That's not allowed inside a square bracket. But inside the parentheses, everything is still considered as continuous time. So that's the difference in notation. Okay, did that answer your question? Thanks for the question. Okay, any other question right here? Any question from the back of the classroom? Okay, you can always come to me after class, right? So, but here is a nice distinction of our notation: continuous time, discrete time. But everything is put together with either this expression or that expression. Okay? The emphasis is different, okay? But we are talking about the same thing. So now we can finally consider using this expression, and we are going to make a substitute that into convolution. Okay, so now we are going to study what will happen when we convolve. Let's call the result X reconstruction because that's our purpose. Our purpose is for reconstruction. R is going to be defined as we take our signal after sampling and convolve it with h of t. But then what is here? Here we are going to use this expression, okay, to substitute. 代入, substitute. Well, summation n, x bracket n, delta of t continuous time, t minus n times sampling rate. No, sampling period. We're going to convolve this with h of t. And next, let's put ht inside. And we can do that because convolution is linear. Right? Because convolution is linear, we can put h inside. So we're going to put h inside. So we have xn delta of n, t minus n period convolve h of t. And I'm going to here put the parenthesis in here. Put the parenthesis in here because as far as convolution is concerned, x of n is nothing but a scaling factor. And again, because convolution is linear, so I can put a bracket around right here. Yeah? Now we're almost done. Okay, we can almost take a break. Yeah. So this is just nothing but reorganizing the summation and convolution. And because everything's linear, you can make some arrangement. 会做一些调整啊. You can make some arrangement because everything's linear right here. And does this look familiar? There's something that we can apply right here. When we convolve a signal with delta shifted to the right by so much, what's happening? We shift that signal, correct? We shift that signal exactly the same amount. Okay, so the result now, finally, the result we get, okay, here, the result that I want is this expression, and we will take a break. Okay, the result I want here really is h evaluated at t minus n times sampling period and summation over O n. So we'll take a break and we make a sketch after the break, right? Now. Hello, hello. Yeah? Can we get back? Yeah. Okay. Um, yeah, first I may need to make a correction, okay? I may. But it's not, hopefully it's not that important. So regarding the definition of Sinc, so one of you just reported to me that most of people in the world define Sinc differently. So I was told by this nice student, a nice guy, that in most other texts, Sinc theta is defined as sine pi theta divided by pi theta. Yeah, so let me go home and make a correction. But either way, this result should still be correct. Just to play safe, just use the standard sign over some this notation. Okay, that's probably less controversial. So I apologize if I make a wrong usage right here. But this just will still be correct. So what we're going to do next is to convolve this function, which I do call it Sinc. Okay, because in principle it's the shape of a Sinc function. Yeah, we are going to now. Yeah, now in the last 10 minutes ago, we reached this final expression. We reached this final expression saying that which tells us when we convolve the string of spikes, each modulated with a height of hx bracket n, 中括弧 bracket n. Then the result of convolution can be expressed as a summation of h on the right, of that h function, that h of t shifted to the right and modulated by the same height. Okay, and we sum over everything right here. Okay, we sum over all n. Okay, so now I'd like to invite you to work with me. Then what is the result of summing of this summation? We're going to sum infinitely many copies of the impulse response, each shifted to the right by so much. Okay, yeah. So okay, so let me collect a few chalks. All right, so let's consider the first spike right here. The height is x0. And we are going to put h of t with n equals to 0, right there, right? N is 0, h of t. So we are going to put a copy of h of t right here. And where h of t, which looks like a Sinc function, should go to exactly crosses 0 at 1t, and then it goes back and crosses 0 again at 2t, and do this, and smaller, and so on. So that's the first. This is h of t, but with the height multiplied by the height x bracket 0. Okay? So the first thing here is one term. So now I'm going to draw a few curves, and each curve will correspond to one term in this summation. Okay? That's what I'm going to do. So the next curve I'm going to draw is what if n equals to 1? N equals to 1, we have the height of x1. And I'm going to also put a copy of h of t, of the impulse response, which looks like Sinc, but shifted to the right by one sample. Right? So we're going to draw a copy of the Sinc function, but with a slightly higher height, slightly taller, but which is slightly taller than x0. But now another copy of the Sinc function going further down, slide up and down, and this is down right here. And let me draw two more. Okay, so similarly, at time 2, we are going to put each one term correspond to a copy of the Sinc function with different heights. So now the height is x bracket 2, right? So we are going to put a sinc function right here, which should be about the same height as x0. We promise. So it will probably look like that, something like that. And what else? Probably look like this height. And so on. Okay? And now, similarly, next, you can do it by yourself. And with the height of x bracket 3, we put a copy of the sinc function, which crosses 0 at exactly the next sample time. And that, and something like that, like that. So that's what we're going to do. Okay? That's what we're going to do. Similarly, just everywhere we have a sinc function. Everywhere we have a sinc function, and so on, and so forth. And so on and so forth. That's kind of a sketch I'm trying to make. I'm trying to make a sketch to visualize what's going on when we do this summation. And this summation is a result of convolution, of convolving the spikes with our impulse response. Okay? I'll claim to you that convolution here is the result of filtering. So when we design a filter, that filter using any sort of hardware, this is continuous time analog filter. Okay, so conceptually, this is what's going to happen back in the time domain. Okay, back in the time domain. So can you now sort of put everything in your mind? Try to see what will happen when we add all the curves together. When we add all the curves, when we superpose all the curve, when we superpose all the curve, the result should be this. The result should be a reconstruction of the original signal. The result should be exactly the same as the original signal after reconstruction. So hopefully this allows you to see, to make sense of it. Okay, to make sense that when we just put all the sinc functions, add them up together, the result is a reconstruction that should be the same as the original signal. Okay, and we can believe so because in the frequency domain, their spectrum are identical. Because when they are same, when the reconstructed spectrum is the same as the original one, then using inverse Fourier transform, they should be the same. You should expect them to be the same in the time domain. Same in the frequency domain by design, same in the time domain consequently. So that's how reconstruction can happen, okay? As long as our bandwidth is finite to begin with, and we sample at 2 times higher. Sample at a rate that is at least 2 times higher. Right? So I'd like to kind of stop for a while and to give you some time to think to contemplate what's going on. 凝视一下, contemplate, okay? To contemplate what's going on right here, same in the frequency domain. Therefore, we expect the result should be the same in the time domain. And by plotting, it sort of makes sense, right? Low-pass filter. What is low-pass filter? Low-pass filter is to make everything smooth. Spikes to begin with, but smooth as a result after low-pass filtering. When everything's designed correctly, you expect to get back the original envelope. The original signal in continuous time. Okay, okay, so that's an exercise that hopefully I try to demonstrate to you that you can make a sketch, you can draw a sketch of this convolution, and the result is simply adding all the sinc functions. And I say that this operation is an interpolation. It's basically you can call it sinc interpolation. Why? Interpolation 内插 interpolation is when I like to use interpolation is when we measure something like in time, in discrete time, and then you try to figure out what happened in between. That's interpolation, right? For example, this is our GDP, right? GDP of Taiwan 2023, 2024, 2025. 2000, no, not GDP. Oh no, GDP is not a good. I try to example something that will vary. Give me another example. Interpolation. Come on, let's try to. Can anybody tell me an example of sampling something? And we often need to figure out what happened in between. Well, that's interpolation. 温度. Okay, that's good. So this is temperature, okay? Temperature in Celsius. Okay, so in the morning, 6 o'clock, we have a temperature. And 12 o'clock, we have a temperature, right? And 18, we have a temperature. 24, that's the next day. We have a temperature, right? That's a very good example. Thank you, right? So you take the measurement of the temperature outside every 6 hours, and you ask, what's the temperature of 9 o'clock, at 9 o'clock? What's the temperature at 4 p.m., around right now, okay? Yeah. So that's what we mean to do interpolation, 内插. So as long as the temperature signal is band limited, right, we can perfectly reconstruct the temperature at every moment. That's what it takes a leap of faith to believe this bullshit. As long as the temperature is time limited, not time limited, band limited, then we should be able to make a reasonable interpolation. What's the ideal way of interpolation? That's what we're talking about. As long as the temperature signal is band limited, then the ideal way for interpolation should be using sinc. Okay, a less ideal but more intuitive way. There are many other options, right? More intuitively, what if we just make linear interpolation? Does it make sense? It makes some sense, right? 6 to 12, yeah, linear interpolation. 12 to 18, linear interpolation. Yeah, it also makes some sense, right? But here we are suggesting that in the context of digital signal processing, using this language, the ideal way, which introduces no spectral distortion, should be sinc interpolation instead of linear. Okay? Yeah. Right, are things making sense? What does it mean to do interpolation? Okay? To figure out the missing information when we are not making the measurement. Okay? And here, in the context of DSP, is about reconstructing the original signal in continuous time. Okay. Now, thank you for the suggestion. Now, all right. So let me move on in the slides. So now, sort of to summarize, using a flow diagram. Okay. So in the textbook, you'll find that this is the Sinc filter that's called ideal reconstruction filter, the sinc function. Yeah. With ideal response in the frequency domain, sinc function in the time domain. So what's in this chain of signal processing, we begin with samples on the left. So that's the input right here. When we take the samples, then by specifying the sampling period, we can convert it to impulse train. This is what's called sequence of impulse train, or what I call the spike train. Okay? We can convert a sequence number into sequence of impulses. And then we apply filter to the sequence of impulses. The result is a reconstructed signal. And the entire thing here, if we just put everything together, is called discrete to continuous time conversion. Okay? A D2C converter consists of first step and second step. First step, second step, and the entire thing here is called an ideal reconstructing system using the Sinc function, right? And that's the notation with D2C box. And you do need to specify the sampling period, okay? Yeah. So far, so good? Does it make sense? Just a flow chart. But here are a few more remarks I want to make before we conclude this lecture. The second remark is now we are in a good shape. So now, so far we have introduced C to D as well as D to C, right? So just you can start with any continuous time signal in the world. Define your sampling period and convert it to discrete time, the result being a sequence of number. And you can as well just when you are given a sequence of number, you can convert it back to continuous time. We can perform C to D conversion, we can perform D to C conversion, right? So this entire plot is about just processing our signal in discrete time. The signal any signal in the world is continuous time to begin with. But now with C to D and D to C, we will be able to do some calculation in the discrete time domain. Okay? While when this discrete time system is put with C to D and D to C conversion, then the entire chain is a discrete time processor of continuous time signal. Let me repeat that. Okay? The entire chain of action now, if you think about it, is from the outside, it appears that the input is continuous time, and the output is also continuous time. So both the input and output are in continuous time domain in the world. Okay? While the actual computation can happen in discrete time. And that's much of what we are going to do for the rest of this semester. Okay? For the rest of this semester, we'll just focus on here, assuming that C to D and D to C are both ideal. Assuming that we can, make the conversion. There are certain circuits that you can purchase, and you can use. And we are going to assume that C to D, D to C are both ideal. Okay? Are both ideal. And the rest of the semester, we are going to focus in the middle, because we know that when we put everything together this way, the result is a processor which takes continuous time input and produces continuous time output. And there are many examples, right? Like in music. The input might be your guitar, your electric guitar. The output is from the speaker. Right, but everything in the middle is digital processing. Okay, is possible. Okay, so input is a vibration of a string, 弹吉他嘛, the way you play the guitar. The output is the sound from the speaker. So as a user, you feel like everything is analog, right? You don't need to know DSP in order to play the guitar, right? But the input and output are both in the world, in the continuous time world. Okay? So that's called discrete time processing of continuous time signals. Okay, so the rest of the semester, we are going to follow this framework and study only what's happening in the middle. Okay, So I have a kind of a discussion item right here. What are the advantages? Why don't we just keep playing the old guitar without using digital processing? What's the benefit? What are the advantages of moving the system to discrete time? Yeah? 比较容易 is easier. Any other suggestion? Does it save the energy, save the earth? Probably, I'm not sure about that. Yeah, so there are always different purposes, right? Probably I agree with you that in this entire semester we are going to see over and over again that discrete time processing is really more simple because you don't need to know semiconductor. Right? Everything's math, right? You hate it or you like it, everything's math right here from now on. You don't need to consider VLSI design issues, and area and energy, nothing. So that's the difference between digital and analog. Right? So that's advantage, but the disadvantage might be energy consumption, right? So yeah, be creative. So probably the best system is a combination of analog digital. But this semester we focus in the middle, okay? Discrete time processing of continuous time signals. Yeah. But it's always good to come back to this question and just question yourself, what are the advantages of going digital? Okay, what are the advantages? Yeah. Just let me conclude with this final slide. Okay. So I say additional remarks. I'm not going to put these on the test. Okay. But just so you know that in the textbook, from the textbook, you also see this figure, which begin with a discrete time sequence on the left, but then D to A converter. Okay, a D to A converter with, you do need to also specify the sampling period. And from D to A, we haven't talked about really what it means for a signal to be really digital. You need quantization. You need to introduce rounding. Okay, you need to introduce that. But that's probably going to happen next week. Okay, when you come back. But here, D to A converter, just for your information, the result is a time domain signal. But then there's a different version of reconstruction filter that's called compensated. Okay, compensated reconstruction filter, and there is some analog design issues there. So here, let me just tell you, this filter is not the ideal filter. It's probably that's easier for analog design. Okay, ideal filter is impossible to design, by the way. Ideal filter is not impossible to implement. So kind of said there are design issues, but we are not going to focus on that. But if in case you are interested, you can refer to the textbook. Okay. Yeah. So that being said, that's the end. If you are interested, check the textbook section 4.8.4. Yeah, that's over there. Okay. So with that, let's take like 2 minutes rest, and I will switch to my next lecture. I want to switch to my lecture, but let's take a 2 minutes break. So I'm a bit curious. Have you obtained a copy of the textbook? I say obtained. I'm asking because just for unrelated. Any of you from ECS 那个电子院学士班? Okay, so we are going to remodel your 系学会办公室, your Office of Student Association. I'm currently the chair, in case you don't know yet. So just Yihui, Miss Zhang Jian Yihui, Miss Yihui discussed with me that we want to put a bookshelf in the office so that you can pass on your textbook to younger students, to the younger generation. So I really like the idea. Yeah, I mean, if anybody has a textbook that you think you're not going to use anymore in your life, you figure out this course, DSP is not helpful for your life, but you have the textbook, please pass it on to 系学会, so that newer students, your 学弟妹, younger students can use them, right? But I like the idea. I highly recommend you to, if you're interested, to find a copy of the textbook. Okay. In the old time, we asked, student bandai, ask somebody to help buying textbook. Do you still do that? Do you still buy the textbook together so you get discount? 可以打折? Probably not. I haven't seen that for a long time. Yeah. But anyway, one reason I mentioned this is back to this next lecture is going to be about some selected properties, 选择性的. I'm going to choose a few properties of the DTFT, Discrete-time Fourier transform, the DTFT. So we are going to go over, but I choose this. You later will see that I'm choosing some properties to report to you, so that those are the properties that I found that are quite useful, often used in this for DSP. Okay, so that's why I choose to show to you a few properties, to mention to you. But for a more complete coverage of the topic, please check the textbook. Okay, 我要完整化. For if you want to just know thoroughly every possible property of the DTFT, please refer to the textbook. Here we are only going to see a few properties. Okay, but before we see the properties, of course, we see the definition first. So here let's go over this slowly. Here is the definition. Okay? The definition goes that we begin with a sequence. Now things are already after C to D conversion, already in discrete time. So we have a sequence, x bracket n being integers. Okay? So we have a sequence of numbers, and then we can define its DTFT as this using this equation. Okay? Using this equation. So in this equation, there's a summation. X, your signal goes here, and we multiply your signal with e j omega n. There's a minus sign. Okay? And we sum. We calculate this infinite sum. And the result becomes a function of beware of the notation small omega. Okay, previously, we had big omega. Right? But here now in this definition, because n is integer, we use small omega, lowercase small omega, to denote the frequency variable. The result is a function of small omega. Okay? So far so good. So that's the definition. And the result is still we just stick to the same convention, small x in time, big X in frequency. The result is in the frequency domain. We go from time to frequency. And this is the definition of DTFT. Okay? Yeah. So the result of a function of frequency small omega. So now I invite you to first think about the unit of omega. Okay, the unit of small omega. What's the unit of small omega? You can say that small omega does not have a unit. That's fine. There's no physical dimension being hertz or anything. Okay, But if you really ask me, I recommend that we can regard the unit as radian per sample. Radian per sample, because omega really is some kind of frequency. Some kind of frequency. It tells us how much of phase is accumulated when time is advanced by one sample. Let me repeat that. Okay. Omega, it shows up right here, e to the, it's not important, minus j or plus j, but just minus j omega n. J omega n equals to cosine omega n minus j sine omega n, right? So it shows up inside cosine or sine. Omega is right here. So it has a meaning. The meaning is when we go ask the question, when time is advanced by one sample, then the phase right here, omega n, the phase, this is time. When time advances by one sample, then the phase advances by how much? That's what omega means. The phase is advanced from omega n to omega times n plus 1. So delta omega, if you will, the phase advancement, the phase progress, the phase advancement, phase changes, the phase changes by how much? By, well, that's stupid. Delta phase, not delta omega. I'm sorry. Yeah. If we denote phase by theta, okay, phase is theta, time is, yeah, then delta theta equals to omega times 1. So therefore, omega has a unit. It tells us how much phase it is advanced when time is advanced by 1. So therefore, I recommend we can think of the unit of omega as radian per sample. Radian per sample. How much of phase is advanced when you can really talk about this. How much of a phase is advanced when we have a sinusoid, a sine function, and then we ask how much phase is advanced when time advances by one sample. Okay? Omega does have a unit. Okay? It's a frequency. Basically, omega is a frequency. So now, the next question we should agree with is that I invite you really still x of n. In this course, think of x of n not simply as a sequence of number, but as the outcome of sampling. The outcome of sampling, always we think of our signal, discrete time signal, as the outcome of sampling a continuous time signal. Okay? Still that we do this. Okay? That's the way we think about x bracket n. We still think about x bracket n in that it's a result of sampling a continuous time signal. There should be a c here, but I'm being sloppy. So notation 比较随便一点, being sloppy. Okay? So agree with me, but the idea is that think of x of n as a result of sampling a continuous time signal. Then when we do sampling, we need to specify the sampling period, right? So now the next thing I want to bring up is that there is a convenient way to convert between small and big omega. To convert between small and big omega. Okay? Small and big omega. So the idea really is, when we say this is in n is 0, 1, 2, 3, and so on. That's n. But the same plot, you can think of this as a result of sampling a continuous time signal. Now, then that's a continuous time variable t, right? So here, really in yellow, we have 0, 1t, 2t, 3t here, okay? With the sampling period fs being 1 over t, okay? So now, quickly, you can really check to convert between small omega and big omega. There is this relation. Small omega tells us how much phase is accumulated by one sample, right? Big omega, what does it tell us? Big omega tells us how much phase is accumulated by 1 second. It's 2 pi times frequency. That's big omega, right? So big omega tells us how much phase is accumulated by 1 second, while small omega tells us how much phase is accumulated by 1 sample. That's a relation. Okay? So how many samples do we have in 1 second? How many samples do we have in 1 second? That's Fs, right? Therefore, big omega should be Fs times small omega, or small omega is T times big omega. Yeah. So that's a way quickly, okay? That's the way I make my conversion quickly in my mind. Whenever I see small omega, I would ask, then tell me your sampling rate. Tell me your sampling period. So I can be sure what small omega corresponds back in the real frequency in hertz. Yeah, this is a bit quick, but let's look at let's do an exercise. Okay, let's do an exercise. What does omega equals to pi divided by 6 represent? So then what should we ask in response? Show me your sampling rate. Okay. All right, so then I say, okay, my sampling rate is 48 kilohertz. Okay, 48 kilohertz being the sampling rate right here, 1 over t. We have 48,000, 48,000. We have 48,000 samples every second, in every second. And then we are interested in looking at omega equals to pi divided by 6. Then what does that frequency correspond? What's the corresponding frequency in hertz? That's an exercise. Okay? That's an exercise. Yeah, maybe I can stop for 1 minute. So just think about, make a contemplation, and then I will work out. Okay? What does pi divided by 6 correspond when the sampling rate is 48 kilohertz? Do a simple calculation. Okay, now we have 60 seconds from now. Yeah, this is important. This is important. Yeah, just to cover the basic first. Yeah, I really want you to be able to make the conversion. 这个切换 switching between small and big omega is quite important at the beginning. You'll get used to it. Using this relation, small omega, big omega, there's a factor of sampling period or sampling rate. 好, 30 more seconds, and then we'll check our answer. Okay, yeah? Almost there? 10 more seconds? Okay, so then we work on the answer. Okay, all right, so just simply to check your answer, I say big omega is sampling frequency times small omega, right? Yeah. So sampling frequency is 48 kilohertz. Now times small omega is pi divided by 6. So big omega should be 8,000 pi. Okay, 8,000 pi in radian per second. That's the corresponding frequency, the frequency that which corresponds to pi divided by 6 when sampling rate is given as such. But now this is equal to 2 pi times the actual frequency in hertz, right? So therefore, the corresponding frequency is 8,000 pi divided by 2 pi, which equals to 4,000 or 4 kilohertz. Okay, so that's the answer. That's the answer. Okay. So yeah, just do it repeatedly and you'll get it. Okay. So that's kind of the convention. 这个习惯 is a habit. Is how we handle the conversion in this textbook. In this textbook, small omega is for discrete time, big omega for continuous time. Both are frequency, and you do need to use this conversion. Okay? So please make sure that you are familiar with that. Yeah, either for math or for computer programming. Okay, for programming, you need to make sure you understand this. Okay, yeah. So a quick way is still even for this easy result is contemplate. So in my mind, I always think of pi. Pi corresponds to the Nyquist rate. That's the easiest way to understand. Pi corresponds to half of the sampling period. So pi represents 24 kilohertz in this example. That's the way I remember it. Okay, just to share with you, if pi is 24, then pi divided by 6 is 4 kilohertz. Okay, so that's the way I do my quick calculation. But anyway, this is easy, but just make sure that everything makes sense, right? Yeah, just make sure everything makes sense. But otherwise, this definition goes from time domain to the frequency domain. And next, I'm going to talk about inverse transform. Let's talk about the inverse transform, right? Maybe we can erase this part. So here is a result we can check. Okay, so just recall that the forward transform from time to frequency is defined as summation x of n, and we make a projection by doing inner product. Essentially, there's a minus sign right here, summation over all n. Okay, now it turns out that we want to check. We can go from frequency domain back to a time domain. Okay, by doing this calculation. 2 pi integral from minus pi to pi, and the spectrum, the DTFT, times E j omega n, and the integral is with respect to the small omega, the frequency. And this expression takes us from frequency domain with the spectrum back to the time domain. The result will be a function of n. The result will be a function of n, right? But we want to check really, does this get us, does the equality really hold? Okay? Because if it holds, then this defines an inverse transform. It takes us from the frequency domain back to the time domain, right? So I claim that this is correct, so that we need to check. We need to check. Okay? But before we check, you can realize that everything is very similar to continuous time, the original version of Fourier transform. Okay? So here still there is the integration, right? But now the range is from minus pi to pi. Okay, we'll see that. But the idea is still take the spectrum, because the spectrum tells us how much of a signal we have at that frequency. Spectrum, right? Spectrum means frequency domain. How much of a signal do we have at that exact frequency right there? So if omega, for every frequency we have a component whose magnitude and phase is denoted by this complex number, then this is the way we put everything back together. So it makes sense. This is some people also call this a synthesis equation. Okay, so this can be regarded as a synthesis 合成的 synthesis equation. It's in the textbook. Synthesis equation. Because we start with the spectrum and then we go back to a time domain by putting everything together. It's like making sound, making signal, right? So it's also called a synthesis equation. The idea is to collect all the terms in the frequency domain, and then each term has a magnitude like that. Each term in the time domain should look like this. Then we collect everything by integration. Okay? 2 pi needs to be there, and we'll show it. Okay? Any questions so far about how to interpret going back to time domain? Okay? So it makes some sense, but we can completely check this. Okay? So now just let's check. Let's check. Okay? So here we don't know for sure, but here let's just copy 1 over 2 pi here. And then what do? We need to substitute this by the definition. We not need to substitute the spectrum by its definition, right? So the way we check it is still keep the integral here, but make the substitution x equals to summation. And just to be smart, I want to rename my summation index. It's a dummy variable. Okay? xm e j omega m. Just not to confuse with the n right here, and this is important. Okay? We don't want to confuse the summation index, which is dummy. 就是叫什么 dummy 哑巴的 which is really just a summation index. And you don't want to confuse this n with that n here. That n here is a constant as far as this expression is regarded. Okay, so please be careful. Let's try to change the summation index from n to m. Okay, to avoid confusion. And this is important. But that's simply substitution. Okay, this is simply substitution. And then we copy this thing right here, e j omega n, and we integrate with respect to omega, small omega. So far, so good? Huh? What's next? Every time you see integration and summation, you can try changing the order. Okay? Changing the order, assuming everybody's happy right here. Okay? Nobody from math department, okay, to stop us from doing this. Summation outside, integral inside. Let's try this. It might work. So summation outside. Now inside we have xm. Just copy everything. E to the minus j. Now we have these two terms. Now becomes both inside the integration. Okay. So here we do have combine the two terms. E to the either minus or plus. Plus probably easier. Plus j omega n minus n. And still we have the integration. Okay? Right? Changing the order. Okay? But when we change the order, we realize that this term does not depend on omega. This term does not depend on omega, so what can we do? Move it to the outside, right? So we're going to move it to the outside. Allow me to erase. Okay, we're going to move it to the outside. Move it to the outside. Xm outside. Small m. Apology for my handwriting. Now integration goes here. And we know how to do this integration. Okay. So now we're almost all set. But now here, we need to evaluate this integration. We need to evaluate this integration where both n and m are integers. M being the summation index, n being the n, okay? N being the time index, right? So now when you consider this integration, okay? When we consider this integration, we notice that it's non-zero only if n equals to m. When n both being integers, when they do not equal, then this integration equals to 0, or it vanishes, 它消失. When this integral is non-zero only if n equals to m. Can we agree on that? Yeah, because it's cosine plus j sine. Both are periodic, and n and m are integers. And this integration is with respect to omega, not nom, right? So let me just make a note that you want to note that this equation, this integration, equals to 2 pi when n is equal to m. When n equal to m, this becomes 0. We are taking the integral of 1 in this closed interval, right? So and then the result is 2 pi. Okay? Otherwise, it's 0 when n not equals to m. Right? So now we can continue. Okay? So with this result, hopefully we'll see that every term is going to vanish except for the term that when m equals to n. Okay? So this is now still we have this summation. And now the summation is multiplied by one thing that almost always vanishes. It's non-zero only when m equals to n. Maybe I should write it the other way around, just to emphasize that m being the summation index. That's probably more easy to understand. Okay? So we have an infinite summation, but most of them are, almost everything is 0, except one term. Except that one term when m equals to n. And when that happens, the integral equals to 2 pi. Okay? So when that happens, when xm at m equals to n, when that happens, the result of integration is 2 pi. So therefore, indeed, 2 pi cancels 2 pi, m equals to n. The result is x of n for any n. Okay, so that's a kind of a short check of what's going on. We are given the definition of DTFT, the Fourier transform, and now we do have a suggestion of a formula which gives us the inverse transform. And we have checked that by exchanging the what? By exchanging the order of summation integral, we can show that, we can convince ourselves that indeed, for every small n, for every time index n, this expression gives us an evaluation of our sample value in the time domain. Okay. So we are running out of time. Yeah, we're running out of time. But so now with the definition of forward and inverse transform, you are ready. You're all set for homework number 1. Homework number 1 is going to be due next Monday. Okay, next Monday, 17 p.m. No, 17:00. 5 p.m. I mean 5 p.m. Next Monday. I understand that we have a long weekend, so the homework is not going to do until next Monday. Okay, please be aware of that. Otherwise, please sign up and then just a sneak preview. We do have a few properties I want to go through before we move on. Right, they are going to be useful. But anyway, tomorrow for discussion, and see you tomorrow.